Okay, good morning, people. Nice to see more people this time. Just to check, most of you are from the background of electrical engineering or electronics and telecommunication engineering. Electronics. Anybody who is, let's say, computer science? There are a few. And any other mechanical, biomedical, mechanical, mathematics. Okay. No issues? Yeah, so of course, choosing some topic which will work through everybody is an optimization that's better solved by you guys than us. But let us see if we can take home something for everybody. So that's a plan. So we'll talk about communication and signal processing. In particular, we'll include all the networks, etc., into this common framework. The idea is not to tell each and everything that you can take home, but some aspects that I will say differently, so that this will help you in your institutions when you teach students and alike. So when we say IoT, we start with all these nice pictures of things that we are familiar to us, which includes everything that you are dealing with nowadays, including the mobile phones and TVs and whatnot. Everything is there. Essentially, it's some kind of talked about as a home automation framework, where there is something which is a cloud which is going to sit in the middle, and everything will be connected to that cloud, which will have all kind of devices, your home devices and phones and other infrastructural devices. It is actually a paradise for a company like Google or Amazon, etc., to have everybody hooked into the network. They can sell each and everything that they want to customized audience and make you buy. That's what they want. So it's actually, whether we need it as of now, I don't know. But certainly Google, Amazon, all the big Microsoft, all the big companies need it. So we are going to live with it. But that's the way it is kind of forced on top of us. Right? Are we ready for it? We do not know. But we can do it. It is not such a it is not a paradigm shift or anything like that. It is a amalgam or a collection of the existing technologies put together to a framework, and getting all of them connected to a common cloud is what this IoT infrastructure is about. But what it is not about is that it is not about repair works. Right? If somebody says you have to put these nodes together and see whether it is working or not, certainly that's not a teacher's job. Not even an engineer's job, it's a repairman's job. In fact, what will happen, unless we educate ourselves to the technology behind it, we will end up doing repair work for Google, Amazon, all the big companies. Right? So we should learn what is behind it. In particular, today we will focus on this as one aspect of the IoT problem, where this communication and associated signal processing problem. So we will not talk about anything else. We will only talk about these links. How do the nodes connect, or how communication is established? What kind of signal processing is required? Is it okay if I move around, or okay? Okay, and feel free to interrupt me at any point. Okay, so there are some general purpose information, some information which are technical. So everything is packed inside it, but I will put it in a way that you can take it. I'm kind of hopeful that you will get most of it. Feel free to interrupt. Anything, just stop, okay? Stop me. So we will focus on the physical wireless link. That's our plan. To put it into perspective how much of this is relevant, you might have seen this recent event with what happened with this Chandrayaan, that communication with lander lost. Just to contrast, a few decades back we used to lose rockets, and we used to talk about engine failures, ignition failures, this failures, that failures, mostly of mechanical, aeronautics and things like that, or even cooling failures, temperature failures, things like that. But now those are all, we have kind of overcome all that, it looks like, and we are in the regime of communication dictates what happens to everything. Right? It is the communication. If the communication is there, we can correct for errors, we can correct for mistakes and things like that. So this has become a vital link, and so the same communication is used in IoTs and all kind of networks that we are dealing with. But unfortunately, if you ask, you might have read the same thing in papers, but what do you mean by communication is lost? Anybody here have thought about what does it mean really when you say communication is lost? Yeah, so essentially it is about not getting the signal. Just like your mobile phone with walking into an area where there is no signal present inside that, then you suddenly see a drop of signal or drop of quality. Is that the problem that has happened there?
Actually, it was being controlled on the feedback basis. When the feedbacks are coming on the end, then the controlling signals were given to control that automatically. When suddenly it stops the receiving the signals, it means that if we are not getting the feedback, it's like we are walking with open eyes. Suddenly we close our eyes.
Okay. Okay. So this is all telling about what happens after a communication failure occurs. But what is meant by the failure itself?
The hardware may have damaged.
No, that this is lost was 8 minutes before it, no, or 8 seconds before, even before it hit someplace, right? After that hard landing happened. Yeah, so this is correct. That's all the English words we are parsing it around, but we are not getting to the real problem of what is the throat choking that I was not able to speak.
Sir.
Huh? Sorry. This is all after effects of what once it's lost, right? Unfortunately, if you ask back, many people, including I think from this kind of people who do this, etc., they do not know what is the communication mechanism that has been used. If you look, the difference on the mobile is that if you put the mobile and you take a spectrum analyzer or something, some equipment, and switch it on, you will see that signal, or you see the presence of that signal, right? Because there is power inside that. Whereas something coming from the moon, it's so feeble that you won't even see over and above the noise something has come or not. So we're talking about completely different signal loss about the picture. But people do not know how this is corrected. Then how is communication possible on the first place itself? If you can't see it on an analyzer, what is coming or not, how is that we can get the bits, we can get the pictures and things like that. And that's where our education also misses a lot. Our undergraduate education, entire India, do not deal with these communications or how do you get these things back. None of these problems are covered. We only go through textbook examples and try to work things out. So my objective is that, look, this problem, along with several other problems, can be threaded together to a common theme. And we can use very, very simple, minimal algebra to kind of get the things out. So we have to eloquently mix the problems and the modeling and the solutions. And then we have to educate the student, look, this can be done. It is as simple as what we are going to say now. But any more detail of how it is done exactly is their impetus to go and read and find out, or you have to kind of educate them in a detailed level. We cannot do it in an hour and a half. But I'll try to tell you the exact picture behind this, not this particular example, but in general what happens in communication. Sorry, yeah, please. Yeah, very much possible. Very much possible. We do not know to say. But even when every device is working well, getting communication from a faraway place is not easy, even from a satellite. Though we have mastered the technology by this time, right? But let's see what goes underneath. To understand that, we don't have to go to rocket technologies. In fact, we can come back home and look at our own CDs. This technology also has many parallels to the technology which is used on the other side. Of course, we are not talking about the same signal levels and things like these are different. How many of you know how a CD works? Now, these are optical CDs, optically read CDs. But this CDs, there are thousands of scratches inside this. Each scratch kills all the information on that. But still, when you play your Windows CD or you boot it and get it installed, it works. So communication is lost, in fact, on many points in the CD, in fact, thousands of points inside the CD, but still we are able to get things back. If we can understand that mechanism, we'll be able to understand the mechanism on the other links or any other link as well. Okay, so I'm going to use the example of a CD to kind of tell you how communication or signal processing is done in an error-free manner. Okay, turns out that if you learn this too, there is a third one which gets for free. It's like, buy two, get one free. If you understand the two ones, here is one which is for free. This is the idea of medical imaging or magnetic resonance imaging. Uses almost the same ideas that we have to use in the other communication. Right, so the same technique we are going to use the same lever or same screwdriver to remove 3 screws and understand. Okay, we'll focus basically on the second example, the CD example, because all the vital components are there. Okay, so here this is more of a signal processing example, in particular a sensing example, where you want to sense something which is inside this column. Okay, so the ideas here can be used in sensor networks and a lot of other problems also. So I just use this as an example to just tell you that, yeah, you can learn all this in one shot. Okay, are we ready for this? Any questions? Feel free to shoot, no problem. Okay, turns out that this one single simple problem is the crux to solve all that. This is a simple puzzle, a puzzle of picking the odd one out. What we have shown is 10 bags. Each bag has 10 coins inside it, and each coin weighs 10 grams. Right, so it's 100 grams in each bags you can see. All except one bag has 10 gram coins. One bag has 11 gram coins. Is the setting clear? So these are the bags. They have 10 coins each. Each coin weighs 10 grams in every bag except one. In one of the bags, all the coins are 11 grams. So the total weight of that bag is 110 grams. Okay. Now I want to pick the odd one, the one which the 11 gram coins out. Can people suggest ways to pick that?
Third one.
Third one. No, it's not, no, here I have marked, I am just saying that there is something, I don't know, this dots can be anywhere, right? Sorry to kind of, confuse you by this picture. It's just saying that somewhere there is a bag, right? Now, because you can't now tell it, because I have shuffled things around, so you can't tell it, so I allow you to open it and look also. You can open any bag and look. How do you find which bag has 11 gram coins? Yes, please. Good. Then we'll answer that later. Good. Okay, so the standard way is to check. You can check. You can take a balance and check which side is heavier. So in a log 10 searches, that's roughly the number we are saying, you will be able to figure out what the number is. Right? So this is a logarithmic search widely used in many problems of fault detection and things like that. But here I'm going to help you. I'm going to give you one weighing machine to measure this. So you can take a weighing machine and you can put the coins there and it will show you the weight. You can put the bag also, but bag's weight I don't want to. Right? So you can open, say bags are weightless. Fine, no problem. Okay, plastic bags. Anyway, so but the problem is I will allow you to measure only once. You can get the weight reading done once. You have to tell me which bag has the heavy coins. 10 bags. Yes, so you clear, then weight will be clear that it will be 100 into 10 plus a 10. Right? Sorry.
Going to put one by one to the same.
You can only measure the weight once. So if you do that, you get weighs again. If you go to your colleges, ask the students attending final year placements, they will know the answer because this is a typical question in many of those aptitude exams. Right? So even before I say the question, they know the answer because they already prepared everything for that job. Okay? If the question is not clear, please tell. Question is clear? Please suggest answers. Sampling. I didn't hear it, sorry. Sampling. No, sampling may or may not work. Now we have to attach a probability to it. We don't want to do that. Yes. Yeah.
And we mark each and every coin from which bag we take it off.
Yeah.
And if we will put that, then in that case, if the resultant error, what we have to get is 100, and result we will get 101. Then we know that there is an error, and the marked coin, what it has, then we can say that we got from that bag.
It is a good thinking to start with, though not complete, right? So it's a good thing that if there is a heavy bag, you can find out for sure by this, right? But then I'm telling you in advance, yes, there is a heavy bag, so you don't have to check this. Your weight will be, by this mechanism, it will be 11 grams. Sorry, 10 into 10, 101 grams, right? 101 grams, right? So there is now, given 101 grams, you don't know which bag it is. So the strategy fails at that point. So you have to, you have the idea, yes, if you work it, you will get the thing. No, they all look alike. Yeah. Yes. If you go to the railway station and there is one, put a coin, you give a weight. 4 of you stand, take one out, then take one, you can get 4 ways. Is it true? No, you can't. That coin is for one reading. Okay? Yeah. Yeah. It has to be read once. Yeah. More ideas? Please.
One coin to another bag and weighing at a time 2 bags. It gives equal weight.
But then now it's just 2 bags. We have 10 bags, no? Just be more generalized. This is actually, there's a principle there. What you say is that when you focus on only a small set of bags, that information may slip out of your hand. So our focus should not be on a set of bags. It's a very good principle actually to use. I'll now give him he knows the answer, so let him say the answer.
Sir, if suppose bag are numbered from 1 to 10,
yeah, like this.
Then you have to take 1 coin from bag number 1, 2 coins from bag number 2, likewise 10 coins from bag number 10. If all coins are genuine, then the weight must be 550 grams. But now one of the bags contain coins with 11 grams. So we have to check on a weight how much grams it is more than 550. So if suppose the weight comes out to be 555, then it is obvious that bag number 5 contains the coins of 11 grams. If it is 557, then bag number 7 will contain like that.
That's precisely said. That answer is a precisely said answer. You can take 1, 2, 3 up to 10 coins from each bag. If all of them were 10 grams, you will get 550 grams. The first one had a heavier one, you will get 551. Second one had heavier, you get 552, and so on and so forth. Exactly the idea. So you can find the bag number by using this one measurement. Once you get the idea, it's a very simple principle. You just put them together, and look at the weight. Mathematically, what are we doing? We are doing something called linear combination. We are just taking a linear combinations of those values. It's either 10 or 11, and then for different coefficients, we are taking linear combinations, right? Where AI is I in this particular picture. You see that we are doing just linear combination of the values, right? And that linear combination has a peculiarity, as Madam there pointed out. The measurement should cover all the bags. If you should not limit yourself to a set of bags, then you may slip out. So your linear combination has to combine everything inside it. Collect information from every point, put them together, right? And then, yeah, linear combinations are good enough to find the odd ones out. So this problem is very much similar to your kids might have picked the odd face out of a, or odd duck, or odd bird, or odd object from a set of objects. Like there are this, the storybooks has this small problems there. It's a very similar problem, except that now instead of taking 1, 1, 1 and checking, we can linearly combine them and do one shot checking. Okay, the idea is clear. If the idea is clear, we are going to generalize this to solve all the problems we said earlier. Okay, so that's the plan. Essentially, this is about solving linear equation. These guys will now close their eyes because these are like baby stuff for them. So we have some linear equations. There are 2 linear equations. How do you solve them? It's about finding a common point of those lines, and so you can solve it by Cramer's rule or so many other rules, right? In particular, if there are n unknowns and n equations, and the equations are linearly independent, we can solve them very easily. Okay, this is standard stuff in any, like I think 9th standard or something like that. How about if we have more equations and less unknowns? More equations, less unknowns. This is again a paradise for this so-called machine learning people, where this data fitting and all the things are being done. In fact, the solutions are well-known solutions are there. This is called the least square solution. It's like because of the importance of ML, many people know the answer already for this, how to fit a curve on a set of points, right? So we can solve, if there are more equations and less unknowns, we know how to solve it, right? So it's a pseudo inverse Bayes solution, very, very easy to find. But the problem that we have seen is that we have one equation and many unknowns, right? Because we had only one equation that we didn't know which bag had the heavy coins. We had to find, so there were 10 unknowns, but one equation connecting them. So in a line, it will look something like that. So every point x1, x2 will satisfy this, this equation there. Which one will you pick? There are an infinite number of solutions. So it seems impossible to pick the correct solution. But fortunately, in the question, I told you already that there is only one guy who is different, or there is only one odd guy. This is the key principle that we are going to use. We have less number of equations, but we will use the idea that there are not many values which are different. There is only one value which is odd, or a few values which are odd values. Use that to solve this problem. That's the idea that we are going to push. Essentially, we have m linear equations. This is a generalization. N unknowns. So you always think of x1 to xn as the vector that we are going to find out. And we have equations y1 to yn. So we can arrange those m equations in the form of a matrix. So y is equal to a times x. This is n dimensional, this is m dimensional. M is much lower than n, is what we are thinking of. So 10 unknowns, 1 equation, or 10 unknowns, 2 equations, things like that. Right? That's what we are thinking. Now to find the solution, we are going to say that x has only a few odd values. Almost all the values are the same, except for a few odd guys who may differ. Okay? And in particular, when we say sparsity, we say the number of non-zero entries of x. That is because, for example, the bag problem, I can subtract 10 out from everybody. So then everybody is either 0 or 1. So that's why we take the sparsity, or the odd guys are how many non-zero entries are there in the x. Okay, so we can convert the original problem to just look at those x's which satisfies this equation, and with a small number of non-zero items inside it. Okay, now I might have said something more that people, maybe it's difficult for people to comprehend. So I'll give examples starting from this. So our system is the matrix here, n length vector, m length vector here, formed by all kind of, whichever way you like to think, the column space or the row space. We have to do two things. One is to come up with this matrix A, and then say that what is the value of x. So it's clear, you have two things to do. You make that combination like he suggested, 1, 2, 3, 4, 5, 6, 7, 8. That was a linear combination. You have to tell me what combinations to pick. And then you have to tell me how do you say the x from y. Okay, so n length vector from m values you have to tell. Is the problem clear? Now we are going to do examples to make it more and more clear. Please participate with me. This you will get much clearer ideas now. Here is an example. So here n equal to 8 means there are n values in the vector, or n equal to 8 values in the vector x1 to x8. M equal to 1 means you have one equation connecting them. S, we said, is a sparsity which says that there is one non-zero value inside the thing. I give you additional information that the non-zero value is either 0 or 1. So this much is the problem setup given to you. You have to design A1 to A8 and then tell me how will you get x from Y1. I give you a few seconds to think. Is the notation clear? 8 unknowns, one equation, one non-zero value. That non-zero value is 1. What value with Y1? You have to design A1 to A8 and tell me how do you get x from 1. So even if you have not followed the other things, please think on this problem. Yes.
And only one value from A1 to A8 is have any value.
We do not know that. A1 to A8 is your choice. You should tell me. I only know that x1 to x8 there is only one value which is not 0.
1, 2, 3, 4, 5, 6, 7, 8.
Good. Yeah, very good. So imagine this way. So maybe I told I'll give him the chance. Yeah, you can tell that.
Sir, my argument is that for I varying from 1 to 8, AI must be equal to Y.
Yeah. So that is
you
one.
can form any array.
Yeah, that's correct. So that is correct. That's exactly what he was also suggesting. But let's look at the underlying principle of that. If x1 is 1, what will be the answer? A1 will be the answer, right? Because we product x1, A1, all others will be 0. A1 will be the answer. If x2 is 1, A2 will be the answer. You should be able to differentiate between A1 and A2. So A1 should not be equal to A2. If A1 equal to A2, gone. You can't do that. So the simplest choice for different one is, as both of them suggested, you can use 1, 2, 3, 4, 5, 6, 7, 8. But you can use any different values as well, any order, nothing matter. Right? As far as we can identify an index with a number in the matrix, you are fine. AI not equal to AJ is all that you need to find any such vector. Is the idea clear? Right? So now we are going to, so we need just one value. Look at the value, we know what the index is. Okay. Now we are going to make it complicated. Okay. One step complication. Now I am saying x can be any value from 0, 1, 2, 3 onwards. Any non-negative. In fact, I can make it negative also, but let's say any non-negative value. If you want to think, you can just think up to 9. That's also fine. But instead of the earlier one equation, I allow you to take two equations. So that's why m equal to 2 we have. Same problem, m equal to 2 means you have two equations. But our unknowns are not just 0 or 1. It is 0 or any other value. But at best one non-zero value. It can be 100, 10,000, 999, but only one non-zero value. It is this step which will decide how we take this further and further and further. And we can solve all the problems that we said earlier. Right? You see, every time I push a little extra, but it will be moving close to the heart of the problem. Is the setup clear? Please try, it's okay. I mean, be brave and try. Fortune favors the brave. I can give a clue also. Use the principle that I said earlier. Suppose x1 was 1. What will be the output? It will be a vector a11, a21. First column will be the output. If x2 was 1, second column will be the output. You want to differentiate them. So the first column should not be same as the second column. You need more. 2 times the first column should not be same as 1 times the second column, or any combination of one column or any scale of one column should not be same as the scale of any other column. when are two vectors related by a scale? You have one vector, another vector is a scale version. When are they related like that? When they are collinear, they are in the same line, they're part of the same line, then you can multiply by a scalar and get by a constant value and get the other vector. So now tell me, how do you choose these vectors?
As prime numbers, that will solve the problem. Miss A11 should be a prime number, A12 is a prime number, A13 is prime number, then that will be solve the problem.
Look, the problem with this, what you said is that suppose there is only one row. Will your answer hold?
Yes, sir.
That's the problem. Suppose you put prime number 3 in the first value.
Okay, sir.
And your x took the value prime number 5. And you put prime number, let's say 5 in the second value, but your actual value took 3. In either case, you will get 15.
Yes.
You are there, but you need to tweak. You are there, you need to think. Yeah. Please, more suggestion. Because this, if you get this step, we are going to reach all the way up to what, moon or Mars, wherever it is. Look, no column should be collinear with any other column. That's all. His idea of taking primes was just to say that your scale should not match the other. That's right. But you have to think in vectors. How do you take 8 non-collinear vectors? Basis, 2 dimensions, for example, how many bases you can have? 2, no? You need 8.
Values.
No, don't go to, nothing complicated here.
They should not be collinear. That is there. I mean,
Regression, etc. are the final words in our thing. We will not
That's
even
how
use
we
that.
remove the collinearity in a vector.
No, why do you even move it? It's up to you. Oh God, this is going. Okay, so it's up to you to design this. No. Is there a chalk piece? Yeah. Right? So all we are saying is that, look, here is a, suppose I take my first vector like this. That's my first vector, that's the first column. Where can I take the next vector? Anywhere. So I will take here. Where can I take the third? Anywhere. That's correct. If it's 8, I don't know. I think so. Yeah, 8. Okay. Take those vectors, put it into the columns. You scale anything by any number, it is not going to hit the other. Done. Now, if you are from electrical engineering or telecommunication background, you will see the basis of nth roots of unity appearing in what I am saying. So there is a whole connection which dives deep to Fourier transforms. We will try to unravel it as we go on. Okay, but those who are not familiar, don't worry about that. Right? You may get something more, but it's all about taking 8 vectors non-collinear with respect. Idea clear? Any questions at this point? Okay, so let's go. We are going to, now nobody suggested, I said don't collinear, but what's the easy solution? It's near his prime, but prime in terms of these vectors we are talking about. So you can take a very simple choice. First one is all ones, second one is 1, 2, 3, 4, 5, 6, 7, 8. This will ensure that no scale matches any other thing. And this is the simplest one also. I use this because there is a very strong structure in this thing, because you can think of this as 1 raised to 0, 2 raised to 0, 3 raised to 0, 4 raised to 0, etc., etc. This is 1 raised to 1, 2 raised to 1, 3 raised to 1, 4 raised to 1, etc. Those who have Fourier transform will e power minus j 2 pi over n, e power minus j 2 pi over n times 2 and things like that. All of them has this very nice structure which is inside. We can use that to build and generalize. Okay. Is it clear how the answer of this problem comes? The first one, the first product will tell us what is the, this one will tell you what is the non-zero value. Once I know the non-zero value, I can divide my equation by the non-zero value, and then I am back to the first problem, right? Because it's now either 0 or 1. I divided off the value, so the non-zero value became 1. Apply the first problem set. Yes, please. Yes. Yeah.
So then the problem will also be solved by prime numbers. Yes, sir, because I am having distinct prime number for every set of the value. So Aij will be a prime number.
Yeah, but I told the answer to that, no? 5, 3 and 3, 5.
Yes, but X,
We don't know which X it is, no? Think through it. I mean, it's a simple thing to say that. If you have 3 and 5.
yes,
Okay? Now your x1, so look at 2 vectors. Both of them will give the same output. 3 5s, 5 3s. No way to distinguish them.
sir, but other row is also there, no?
So that's why I asked you, I give you only one equation, can you? So then you have to put more things there.
Yeah.
Not about primes.
No, on second equation, I am already having a prime numbers, isn't it?
Second numbers also you
Sir,
have.
second row is also there. On
so
that
what are
row,
you
I am
putting
having
there?
some other number. So the answer will be distinct in both the cases, isn't
Yeah.
it?
So
Yes.
if you make sure that they are not lying on the line,
Yeah.
that is correct.
Obviously, that's why I am saying that all the vectors of A, means all the elements of A will be having prime numbers. So first row is also prime, second row is also prime.
So
That's why.
maybe there was a confusion because I asked you, can you work with one row or not? Right? So that is why I said. So you can pick anything. It's okay. It's good that you have found. Okay. Any other? Is the generalization clear? Okay. So let's now go to bigger ones. Okay. Now I'm going to put more to the palette. So here I give you 2 non-zero values. Hey, by the way, if you want a challenge, this previous problem, if I limit the values up to 9, I can do in one equation. You can think of it as a challenge, do it later. Okay? If only values are up to 9 are allowed, 0 to 9, I can just do it in one equation. Okay. So now let's go here. So now the next generalization is where we have 2 non-zero values, but I allow you 4 equations. 2 non-zero values, 4 equations. So you have to tell me this matrix that you are going to use and the technique by which, observing these 4 values, you will tell me these 8 values. So every time you observe less, but we will be able to say a lot more. Okay? So that's why n equal to 8 means that again unknowns are 8, m equal to 4 means I give you 4 equations, s equal to 2 means there are 2 non-zero values. Values can be anything. In this case I took up to 9, but you could do any numbers also. So now what's the demand? The first value is non-zero, the output will be this column. Any 2 values are non-zero, the output will be the sum of those 2 columns, or the scaled sum of those 2 columns, linear combination of those 2 columns. So what you want is that linear combination of any 2 columns should not be same as a linear combination of any other 2 columns. Right? If linear combinations of 2 columns is same as the linear combination of 2 other columns, we can say that these 4 columns are linearly dependent, because the linear combination here is giving a linear combination of the other. So you put all of them together, there is a linear combination for which you will get 0. Right? So the idea is that no 4 columns can be combined to get 0, or this will say that any 4 columns should be invertible, because if it's invertible you cannot just combine them to 0 without using 0 vector. Okay, invertible means you are always able to come back to the original value. Turns out that there is a very nice answer to this also. This generalization of the same question that we did, we get 1, 2, 3 like that, but every time we put one more square down. If you take this matrix, any 4 columns you pick, you get what is called a van der Monde matrix. In your +2 classes, etc., you have always found a determinant of this. So it's a very, very easy exercise. The determinant is nothing but take the second row here and find the differences and take their products. If no two columns are the same, they will always have a different determinant, because the determinant is a product of the differences, right? So this matrix will make sure that no 4 columns are linearly dependent, which will ensure that looking at this y, you will be able to tell exactly what this vector is, because the linear combination of 4 columns cannot be same as linear combination of any other column, or 2 columns cannot be same as linear combination of any other. So looking at one, what is y1 to y4, you will be able to tell the answer back. Now you can map the whole problem into discrete Fourier transform. Instead of 1, 2, 3, 4, just use e power minus j2 pi over 8 in this picture. Everything works out. It is just saying that any vector which has 2 non-zero values can be found from 4 Fourier coefficients. That's all it is saying. For example, if you have just an impulse, the Fourier transform we know is a flat line, and there is only a phase component which is missing in the thing. So what we are saying is that we can find from 2 Fourier coefficients wherever the impulse has occurred, right? From 4 Fourier coefficients, we can find out wherever 2 impulses have occurred. That's exactly what we are saying. Sparsity, in a sense, is the number of impulses that you are talking, right, of different values. Okay, so that's a way to solve all these problems. And there is another challenge I have given. If anybody wants to do it, this will be a very nice challenge. Here the problem is that 8 cube is 1024, 2048, no? 256 into 8, okay, so 2048. Suppose I only want values up to 10 in this matrix. Still I should be able to recover x from y. Can you design a matrix with values only going up to 10? If you can solve this problem, this will take you to the realm of finite fields, right? So if you have anybody worked with finite fields or anything like that? Okay, yeah, or even our binary arithmetic is a finite field arithmetic. It's a GF2 that we are talking about. So this is a clue, or this is a, if you can solve it, actually you have gone much deeper into the problem of finite fields and error correction codes, and you'll be able to apply these techniques to communication problems, etc. So this is a good problem to work on. Okay, 0 to 7. Please check that out. Please check that out. Write a small program which can check it out. Every 4, so 8 choose 4 combinations are there. Each of them should have determinant non-zero, right? Which is not clear from that suggestion. But there are other ways to solve that. If you understand the word finite fields, you will know what we are talking about. Right? Finite fields is that the field does not blow like integers or real numbers. We stop it. Modulus 2.
And then it will be like either 0 or 1, and just so whatever it is. So if 8 to the power 3 modulus 2, 7 to the power 3 modulus 2. So that will be my new matrix, and that will become my.
Nice idea. Unfortunately, it does not work out completely. Though it's a nice idea. It's there. It's a half the step through. You need one more step to get there. Binary it won't work. There's a lot of combinations that go to 0. That's a problem. Okay. Okay. But you should look for higher fields, not binary. That's the idea. Okay. So we now have a reasonable understanding of how to get these matrices and how to solve this equation. If you understand DFT, discrete Fourier transform, that's a clue. You can use it on all these problems. So to recap, we have y is equal to ax, and where m is number of equations much lower than the number of unknowns, and we want to get x back from y. It is typically an underdetermined system. That means less number of equations, so there's no big hop. But if x is sparse, we should be able to get it back. That's the trick that we are going to use. We have design A and a recovery strategy. Okay, so this is the framework of all these problems. It can be applied in communication. It can be applied in IoT sensors, sensor networks where you acquire things. It can be applied in magnetic resonance imaging. It can be applied in CDs. It is used in Saturn props, whatever we said, Cassinis and all the space props that we use have the backend idea. It is used in hard disks, same idea. So the same linear combinations have a lot of applications. At the end, it's a very simple linear combinations done correctly, that's all. And there is another application entirely different from this, but widely used. I thought it will be informative to you, so I have posed this problem. So this problem is called group testing. So imagine end soldiers who come after a war. It used to happen, it's a real application. Once they come back to the parent country, they have to be sanitized in the sense that they have to do all the tests from yellow fever, hepatitis, AIDS, all kind of tests has to be done. And then every test is cleared, they will be let go, you can go to the family. Right? And it's true because in the countries where you are in, what kind of diseases you get, you have no idea. Okay? And you don't want your society to get infected with all that diseases which are new. Right? So you quarantine and you do the test. So what happens is that you do one test, look at the result, you take another test, things like that. It used to take months for people to go home by the time the next war would have started. Right? So this was a problem on all times. So what we want to do is that can we quickly identify the infected parties? So suppose for a disease, we want to quickly identify in the old set who all are infected. 1 means infected and 0 means not infected, or you can give different levels. 1, 2, 3, 4 are the different levels of infection, 0 being none. So we want to do it quickly, fast, so that people can go home at the earliest if they are free of any disease. One simple, easy trick that is used even in lactometers and milk adulteration things is to put all of them together, do one test. If everybody is free of disease, everybody can go home. If the old milk has no problem, no adulteration, then all that batches are clear of problems. Widely used. In fact, Ranbaxy, Bombay uses this same test if you go for an ELISA or any of those tests. Very costly tests. So they put them together, pool it and do once. Okay? So question is that now that's not enough for us. We have to say who all are having the disease. So a few odd values, like for example 8 samples, 2 guys who have disease, we don't know what quantities, we can use the same trick as above. Right? So this is very popularly, or in fact from the time of Fisher, UK and Ireland and places like that, torn with wars, this was applied. And this is called group testing. The same kind of ideas. You want to find a few odd ones from less number of equations. And now the big factor which plays into our hands here is that earlier we used to wait for the result of first test before you doing the second test. We didn't do that. We were doing one matrix multiplication, means all the tests were done parallelly. And we got m values to us. We can decide. We don't have to wait for one test and then do that the next one. So this made huge savings in the blood testing and the time taken to go home, etc. So made a lot of difference in even today in many of the medical testing facilities, etc. These techniques are used. Okay, so a lot of applications. Again, it is an exercise of picking the odd people. Let's come back with all this thing to our 3D writing. Okay, here is a CD, and the CD, it's my hand, you can see I've held the CD, but I drew a lot of things on the CD with a marker pen. So as you said earlier, that CD works based on, this CD works based on optical technologies, not magnetic. Hard disk used to work with magnetic technologies. This is optical, you show light, whether it comes back or not. If it comes back, you read it as a 0, otherwise you read it as a 1. Right? And then keep reading this and make out the movie coming to you. So in fact, that one line might have taken tens of thousands of bits away. That light won't come back, or there's a stuck problem there. So the question is, will this CD play? How does it figure out what I have etched out? In fact, it's a real CD. It's with me if you want to check. It has the same movie I showed you in the beginning, the Jungle Book.
See, when we are reading, so it comes in chunks, in groups.
Yeah.
So even if you, so it's one, yeah, so it comes as a chunk of bytes. So some are corrupted, that's the only black marker will do. So instead of 1, it will read 0, instead of 0, it will read 1.
Yeah.
But when you're reading as a whole, block by block, it won't make much of the difference because it can still infer it out. So it will still play.
Yeah, you're right. I mean, that's what it should do. Otherwise, it won't be able to work. Right? So, but how does it do? It turns out that's exactly the principle that we listed of finding the odd values out is the one that CD background or the computer or the CPU uses that technique to read it out of the CD disk. Right? So it's the same trick that we have learned here. So this movie is about what is inside this CD at a microscopic level.
Okay, this is a really intense and special kind of setup we've got here now. We're looking at the actual data of a CD-ROM at 2,000 times magnification. So this is as close as I can go, and I'm sorry if it's a bit dim, but we're looking through a solid surface at such close, magnification. You're not going to get a lot of light, and it's going to be not beautiful looking.
What you see here, like raindrops, are those points. I think this is from the microscopic channel, where they put a microscope into the CD and look at what is red, right? So each dot here, this little dot here, you can think of it as a 1, and a black, you can think of it as a 0. And the CD goes on like reading like that, 0, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, 0, 0, like that. So it on this arc, it keeps reading like that. Okay, so at that level, so each you can see the bit. Now, if you put a hair on top of it, like take a hair and put on top of it, this entire thing will be gone. It's at that level we are talking about. 2,000s of order magnitude bigger we have made this, or they have made this picture today. So what happens is that when you, so the problem is clear, that you keep on reading like this, and you put a hair or some line, the whole thing is washed off. So it's not that the chunks at the level that we are talking about. The whole thing gets washed off, but still the CD is able to tell it exactly back. Okay, so this context is clear. Okay, so now you can realize, so the way we model this, the first question is how do we model it in an abstract mathematical manner, and then how do we come up with physical solutions. So what we do is we first visualize this CD as this kind of LEDs. Each point will emit light or not depending on whether you have programmed 1 or 0, right? So you can, wherever there is a 1, you can think of these are the 1s and the other things are the 0s. And you keep reading like that, 1, 1, 0, 0, 1. Okay, and like that. So a small segment is magnified and shown. So what we can do is that this can also mimic a communication system. Suppose you have one LED and you flash it or not flash it and keep doing at different instants of time. This becomes a live or the light, visible light communication system. So what we say is not limited to CDs, it can model many communication systems, including your wireless and things like that, at an appropriate level, at a bit level. Okay? So this is a generic thing we can do. Scratch means something like that. No, this scratch is not a scratch at all, scratch, at least this much. Actually much more bigger than that's it, okay? And scratches, of course, erase bits. And what is true here is that a burst, some set of values are erased in one go. Not just one erased here, one erased there, etc. A large section is wiped off in one go. And yeah. So what is making it the CD is working worse is that there are also these blue lights. Because the black lights, we know that, okay, we can't read back. So it is some value which I don't know, it's a scratch. Blue exactly gives you the opposite information. When it is red, it will tell you white. When it is white, it will tell you red. So blue means errors. It shifts the values altogether, flips the values altogether. We don't know when we read it's a blue or a white or a red. So blues are a hopeless thing. So even this has to be dealt with in a CD. I'll first talk about how to correct about the red, how to correct erasures, that is the wiping off like that. Then I will introduce you how to do that blue corrections also. Okay. In all these ideas, what is crucial and critical is this idea of that matrix we constructed, which has coefficients, any number, square, cube, like that. And this is very close to what is known as the is a van der Waals matrix. This is close to what is called the DFT, discrete Fourier transform matrix. For those who know, if you do not know, don't worry. It is again just a matrix with the structure that we have used. So here is the way we model. We take the values of the CD and write it down in arrays. So think of this as the first n values, and there's the second n values, third n values, and so on and so forth. And now what happens is that I have data symbols available to me. I have to write on top of this CD. If I write just like that directly on the CD, the moment CD is scratched, that data will go away. So the key is not to write directly onto the CD. Whatever your data is, do not write that to the CD. You take, what do? You write more than what is required. For example, if your k data values to be put onto that n values, what do? You form n linear equations. You form n linear equations. Now what happens? Somebody suppose scratched n minus k of these equations and you lost those equations. So they are all that question marks which have come into the question. So if somebody has scratched n minus k off, still you have k remaining equations. How many unknowns are there? K data points. K unknowns, k equations, you will be able to solve this thing. So that's the key aspect of how the CD solves this erasure problem. Instead of writing data directly, it takes different linear combinations and puts it into the CD values. How do you take different linear combinations? CD uses the same idea as what we had. It takes the van der Waals matrix that we are talking about. Now take a small data, multiply by this van der Waals matrix, you get a number of such values, and you write it on the CD. In particular, what you do is a very easy exercise. You get data, you pad it with zeros, just compute a Fourier transform, write it on the CD. That's all it is done. Right? So this van der Waals equations, etc., are done in an appropriate field because CD cannot write real values. We have to done in an appropriate field. So the Fourier transform on an appropriate field is what is done. Right? So any k values, you will have k equations and k unknowns to be solved for, so you can find the value out. CD does exactly the same. Okay? So this is how it works. And this mapping, what we have called, is called an encoder. So you take k data values, use this map and generate n values. What is this map? You pad it with n minus k zeros, take a Fourier transform. That's exactly how we compute this. Okay, that's as a simple way of generating this. I'm sorry if that mechanical people, etc., are finding it a little. So all we are talking here is that you generate n linear equations. From k values, you generate n linear equations. That's all. Now Fourier transform is very good because there is a very fast way of computing and inverting it. That is why universally it is used on all this stuff. There are very, very fast ways. There are processor chips which built for just doing it like in a split second, right? So that's why it's an extremely useful thing to do. By the way, that's how map of the world looked like, I think 1500s or before the Vasco da Gamas, etc. People thought there were only three parts, Europe, Asia, and Libya. And they thought the ocean was like that, and they tried to navigate the Magellan times we are talking about. Right? Of course, the world has changed quite a lot from that. Okay, so that's the idea. So we take any van der Waals matrix, in particular Fourier matrix is also fine. We can take the data, multiply, pad it with zeros and multiply by a van der Waals matrix. You get the n values, you get the equations that is required. So the details are, the slides are available, the details if you want you can find. So you can, as far as the scratches, do not take off too many of the equations, you are okay. So the efficiency we will say is of the order there, which means that how much part of the CD contains actual information. So if a CD which is not scratched, you are doing so much percentage extra writing on it. But it is required because if you scratch it, you still want to get the data back. So it's adding redundancy. This is the first step. Okay. Now we can talk about correcting errors. Correcting errors also uses the same idea. You take a data value, you pad with zeros, you take what is called, instead of DFT, you take what is IDFT and send it over the channel. And then at the receiver, you compute the DFT of that. So if you look at that, there are no, it's a plain sailing through this, then IDFT and DFT will cancel each other. So you get the data at the output exactly. But if there are errors in the channel, what you can see is that the zeros here will not come out as zeros. Right? If there are errors, the zeros won't come out as zeros. So one look at it, you know, oh, this is error, I should not use this. Or I can use mechanisms to correct it just like the way. How do you find a few odd values out? Using that, you can always find there are some number of errors, we are able to find exactly where they are and we will be able to cancel it out also. Same trick which is used in correcting errors. Now let me come to the last application, or this MRI application that we were talking about. So now the last application perhaps is an interesting application also. So let's take time and cover this. In particular, the error correction and communication mechanism, it was just using the idea of linear combinations and how to invert it. If you cleverly use it, you can realize a lot of communication systems. In fact, the technique that I said is behind those Voyagers and all the props, space props and things like that, in addition to CDs and hard disks. Now we are going to shift to the last application, that's magnetic resonance imaging. Before that, I want to pose a question. So here is an image I've taken with a 10 megapixel camera. It's way back, 10 megapixel was very costly at that time. Now anybody is like, you know, your camera, phone has 50 megapixels, etc. nowadays, right? That time it was very costly. But if you take a 10 megapixel camera and click an image, there are these RGB sensors, roughly generates 30 megabytes of data. And then you use some program to compress it to 100 KB, 500 KB, 1 megabytes, etc. like that. So all these images I think are 500 KB at the end, though it is taken at 30 MB size. So these are like, it's my home where I used to stay. Okay, so then the question comes, 30 megabytes of data CCD acquires, and in the end I get 500 kilobytes or 1 megabytes of data. Where is the data going in the middle? 30 MB at the point that I take it, but when I store it, it's just 1 megabyte. Where is the data? Where is it gone? Yeah, it is not redundant in that the way of redundancy that we used earlier though. It's not reproducible strictly. It is compressible in a way that you lose something but not much. That's the idea of compression. Right? You cannot get back the original one, but you can get a good version of the original one. Not so exact, but sufficiently good for perception on eyes and things like that. Right? So then it makes sense that you use 30 megabytes, then you compress it to get 1 megabyte. So these mathematicians, Terence Tam and others asked this question, 30 megabytes can be stored in 1 megabyte. Perhaps we are doing something more. What is the actual number of pixels required to take this image? That's the question they asked. And any guess about the answer? It turns out that you can use just 1 pixel to take similar images like that. This idea of linear combinations, very cleverly, carefully used, can do this. In fact, there is single pixel cameras available. If you have money, you can buy it. I think it comes under $10,000 or something like that. Many universities have built their own versions of it. So what is this idea which makes this kind of things possible? Again, simple linear combinations, the way we said it and the way we decoded it. Same ideas are being used. Okay, let's see how Tavo and others came up with this idea. So this is an image, a very famous image for magnetic resonance imaging testing, etc. In fact, we can even go back and take, visibilities are low, but this is a test image. It's called Shep log and phantom. Any MRI machine is calibrated with respect to this. First you show this image and you can see all the things, otherwise you adjust the contrast and all the things. So there are several of this, I think this is a little more visible. There are several of these little markers here and things like that. So it's very essential that you see that. Tumors, all these things can be identified by using this. This image is of size 256 cross 256, which means 65536 pixel values are required. How does the MRI get this thing? What the MRI does is that MRI puts you inside that chamber, then orients a particular magnet and a particular sign, RF pulse and a associated reception, and this is for a particular frequency and a particular orientation. So each measurement of that form will give you actually what is called a DFT coefficient, the Fourier transform coefficient. So I have put the Fourier transform on the right side. In fact, I have scaled it up so that it is visible. So every rearrangement of the coil and one pulse passing and receiving, you will get 1 point. Like that 65,536 different orientations and frequencies. That is what you should do. Takes typically an hour, perhaps more sometimes. Typically an hour to get the thing through. So 1 hour inside the machine is a harrowing experience for many, because you can't even put on your Walkmans or anything like that, because that will affect the whole thing. In fact, any metal will get sucked in and things like that. So it is a ordeal that many people are afraid to get into that chamber, right? Recently, I don't know how many of you are from Bombay. There was one of those incidents where this guy walked in with a jug, metallic jug, when the MRI machine was working by accident, but he was just sucked in, dead. I mean, nothing to be done, right? So it's that kind of thing which is happening. So you don't want that kind of thing. Can we make it faster? So Tavo, here the names are Candace, Romberg and Tavo. They asked this question. Suppose I take a blade, slice of this whole picture MRI that the machine gets. This is roughly 10% of the original size. So out of 65,536, take 6,500, throw away the rest. But it's drawn like that. Take a blade and slice it off. And then ask, okay, now if I can get this, it will take only 6 minutes to do the MRI. 10% of the time. So you quickly put him in 6 minutes, he is coming out even before anything is happening. So very good, very nice. So we can reduce the time considerably. But then if you go to the shop, you take a passport size image, somebody just slices it, gives you 10% back. I mean, of course, this is not what you want, no? Because you are agitated. And so they ask the question, how good of the original one you can come? Right? This is the original one, that is the measured one. And what they realize is that these conventional techniques will give you something like this. Of course, no doctor or approved medical authority will certify that image for any use of finding tumor, because then you have to operate every part of the body, because tumors everywhere, right? So of course, this is medically not valid for any kind of consultation or anything like that. So that means it's a lost hope. If you do 10%, there's no way to come back. But they say, wait a minute, let us try something else. And so they came up with this alternate maxima, or a different way of finding out, using the same ideas that we said. How do you find the vector which gave me this measurement? And they used some trick to solve that problem. It's called a L1 minimization problem. And they came up with this image. If you look at that, this image, it is not related to this image at all in the beginning, because they only started with this. They had no clue it was this image. They started from here, they got here. In fact, this very image that I am showing, I have taken the MATLAB code, put this thing in, solve this and putting it up for you. So it is that image, there is no trickery involved. And these two images are almost the same. But from here to here, it was 10% of the image was used, of the Fourier transform was used, and he was able to come to this picture. Here it's a full image was used to come back to this. So with 10%, you can get as good as quality as the original, right? Now this was a fabulous breakthrough that they have come up with, again using the idea of simple principle of Fourier transform, how can you invert the Fourier transform, right? And using this idea of sparseness in the solution. It's called an L1 minimization program. They won several big awards and other things for this work. Very useful thing. This is called compressed sensing, if some of you know the word. So the idea is that you only take 10% of the image, which means that you need only 10% of the total pixels itself. This idea can be even pushed further to make one pixel and then reuse the same pixel using optical juggleries. If you have optical devices further, here it's not possible because it is magnetic resonance. You need to magnetize and take like that. Even here you can work with 10%, but for imagery, other still images, etc., you can work with 1 pixel also. This has been It's a proven technology.
How about this right top image?
Right top, okay. So we know this image and we know this is the DFT of that image. They are related by the DFT pair. So if you take the DFT of this, you get this. IDFT of that, you get come back. So they are related by DFT, IDFT pairs. So if you take a SHEP login and then use MATLAB's DFT2, yeah.
MRI is being done, then how this 10%?
Good. Okay, so maybe I don't know. See, actually, you know how 100% is received. You turn it around, etc. Now, that's good question. I took a blade and cut it off. But actually, it is done is that this one is very convenient for the MRI because it is along one axis, on frequency axis. So MRI, it's much more convenient to take this star-shaped cuts than the full thing, right? Because next movements are, this is only rotations you have to do.
Means we do the gaps between the...
Yeah, you rotate it like a stepper motor. You rotate at different things and take the measurements on that frequencies, right? So it's much easier to take the star-shaped MRI than the original MRI, right? So it's saving is not just 10%, but much, you can even do lower because the time will be faster, right? So this actually is being used in many of the modern MRI machines.
Information will be lost if we will try to save the more and more. The information will be loose.
That is correct.
And a point will become when the information can't be recreated that you had recreated in fourth. That's bottom, right bottom.
Yeah.
A stage may come there, na sir?
That's correct. He is very correct to show that, look, I cannot keep on throwing 10%, then 5%, and 2%, 1%. Of course, I won't be able to do that, because what we realize is that if there are K or S unknowns, you at least need 2 S equations. In every problem we solved, when there are 2 unknowns, I give you 4 equations. 1 unknown, I give you 2 equations. You at least need double the number of unknowns to get the values back. We can show mathematically that if you have 1 value less, then you will have conflicts. So you need at least double the number of values you expect to be in the picture to be able to solve this problem. If I take this MRI image, I can show by any of this wavelet decomposition or etc. that it's 2% is sufficient to store all this information. Essentially, if you take a Haar wavelet decomposition, and 2% of the coefficient is good enough to store all the values.
But suppose there are maybe narrow.
Yeah.
But suppose when we go, I mean, this kind of thing for like a scanning with only a 10%.
Yeah.
But the in between, that unknown tumor may not go into guess actually.
Yeah.
In that the case, how to treat? I
Yeah.
mean, how to identify that tumor where exactly is like?
Yeah. So that's actually a good question also. So let me answer this by looking at this. This will answer it. Suppose I take the original MRI image. This is the original MRI.
We will not any original MRI, just will scan only a 10%.
I agree. Good question. So this MRI image is given. I again take the blade, slice it, and give you this. This is the same slicing I did it earlier. And I ask you, from here, can you come back to this? Even if I put Gandhi's picture there and do this exercise, nobody in the room will identify it's Gandhi. Though we all stare at it every day on our rupee notes. Same image, you'll not be able to identify if I give you that way. Forget the MRI. Some very popular images, you cannot do that. So it's a lost cause. You will never be able to come back to that. So where is the trick? That is a good question because the trick reveals itself. Because in the trick that we used earlier, we did not cut the MRI. Look, I did not slice this original image. I sliced the Fourier transform. So I already took enough combinations of all this. Each point here has a combination of all these values coming into picture. And then I sliced it. So the same idea as we had. There are many bags, but I take a linear combination. I need only one equation. The rest of them can be thrown out. Same thing here. Each combination here has all the values, some effect of all the values coming inside that. So we have to first, that linear combination we have to take and then slice it. That's a trick. It's a very good question, because then now you should realize that what is happening is that information makes its way into each sample that we are holding back in that thing. Right? If we are just slicing the original one, there is no hope. Right? Okay, very good question. Any other questions? Feel free to ask. Okay. So of course this is not possible. So the idea is again to get the linear combinations correct, and Fourier transform is the key player in all these things. If you are a teacher doing Fourier transform at some point of thing, if you can set the background clear, just other than solving x and e power minus j summation, etc. More than that, if we can give a clear picture of what this transform is, what is the underlying metric structure, random amount structure, why is it invertible, that students will be empowered. They can actually learn a lot of new things using the same trick. Look, nobody taught me any of those things in the Fourier way I have explained to you, right? But Fourier transform was taught, and so Fourier transform was learned. So immediately we could see the connection. That's why you may not see this this material in any other notes, etc. Wherever the reference is there, I put it like this paper, for example. I put it directly there. Okay. So that's importance of this Fourier transform and the basic linear equations, etc. If you can get people to solve linear equations and don't be afraid of it, it's almost half the job done in many things actually. Then we can introduce a lot more stuff. I'm sorry I have packed all these things into just 1.5 hours or so, but you can actually do this. This is a final straw. Don't worry about this. I was just showing as a way to say that the modern trend of all this, or the story now continues, is that instead of trying to find out which x generated the y, we can now teach a network to learn it. So the most of the work, or many work, including Google, Amazon, etc., now goes on. Given this measurement, how do you tell back the original? Earlier we used to solve. Look, in this picture, it was clear that it depends on the way you do. If you do it using the old way, you come up something like that. If you do it smarter, you come up something like that. Now, who tells the smarter ways? Is it amenable, feasible? All these questions come up. Because we know that the information is contained in a small segment. How do we get back the original? Turns out there's a lot of work now going on into getting it done using machine learning. Right? So using deep neural networks, you train the network to decode and then make them able to work. There's a lot of work going on in this area of getting this, and quite successful also. Explanations may follow some other day, but that's the point where a lot of focus is on at this point of time. How to build for very large values, how to build effective learning algorithms which can decode and tell you the values. So in fact, even that communication problem is amenable to learning and decoder. We here just to show you that we have actually put all that decoding algorithms for learning for several codes which are used in communication, and they work out quite nicely. So the work is out there. So in conclusion, we have discussed 3 problems. One of space communication, that is essentially the Chandrayaan and things. But then we focus more on the CD information storage and retrieval. I've been fast on some points. That is because not everybody may like all the contents. So I might have skipped a bit. You can ask me back. And third one is MRI imaging. It's skewed that all of them can be solved by one lever or one linear equation solution. They are amenable to machine learning approaches. There's a lot of work going on to that. That's my email. If you have any question or any other thing, you can send an email. I'll reply. Okay. And if you have questions, feel free to ask. I'm here for a few minutes now. Yes, please. The last graph.
Yeah.
This one.
Yes.
No. Explanation. Okay. I was really saying that, look, these are all decoding problems where you get your observations and then you have to tell what the data is. Like the CD, you read something out, you want to tell what the actual data is. There are errors, erasures, etc. You don't care. You want to find that. So you can train a network or a deep neural network to kind of act as your decoder, and then feed him the observed values. It will tell you what the x is. Give him the y, he will tell what the x is. So we have kind of trained it on some of those communication problems. And this is just to show that the best known performance or the very smart or very latest state of the art decoders, you can perform as good as it by just simply teaching it and learning. So there is a lot of scope into that work. There is less explanations. That's why it is not. People do not. It's more like a religion. It works, but you don't know why. That's the problem. Yeah. The blue is the best. You cannot beat it. But the others are just saying that there are various mechanisms you can try to get it closer and closer. So your logic has to go in also. But there is a way to get the entire information back from a small piece. That's the kind of idea that I was trying to say. Okay, yeah.
I don't know whether my question is.
No, please.
Yeah. Most of the problems where we had recovery strategies through discrete Fouriers were for integer values.
Yeah.
Can we have the same thing for continuous values?
See, the Fourier transform, discrete Fourier transform is defined and works on a complex field. So you don't have, you can take any complex set and it will all work.
Okay.
But the finiteness comes only when you want to implement on a small processor or make it work on a small device, right? So there you have to make appropriate modifications. So our theory is in general for complex field, right? So this is finite precision arithmetic and all these things these are problems which have been tackled for so many years.
Okay.
Right. So the real valued idea, nowadays there are floating point DSPs and other things available. So you shouldn't be, it works.
Okay.
Yeah.
Much more advanced neural network models like ResNet and all those things.
People can use all sort of things, but I'm saying that even the best one we can reach by training it appropriately. Right? There are a lot of work going on. Yeah, people have come up with new and new architectures. Particularly on the imaging community, there's a lot of, because those sizes, sheer sizes were too huge. There's communication, we still are talking about 10,000 bits. We can handle those.
Sir, you have taken the MRI image. You are saying that you are using linear equations.
Yeah.
Previous slides. Yeah, that image is after the final image is a lossy image or
okay,
if it is a lossy, then it is one of the disadvantage of using a linear combination.
So this lossy is more a factor of resolution that you
want
to
up to what extent it will be a lossy.
So if you want, for example, you want to blow up an image as big as possible, then of course the digital cameras cannot do that job.
Okay.
There is a level of dot precision that it can achieve, beyond which you are not worried about it. So we are we are not saying that we will look at millimeters.
Because everything is very important to analyze the image in a medical.
That is correct.
Yeah.
But from what I am not a medical expert to exactly say that, but still what I understand is that there is a reasonable idea people have of how large things are. Like a tumor, whether it's negligible or there is size, etc. So this is well within that kind of resolution.
Okay.
You get all the details within that resolution. Above that, even your original MRI cannot do that. Right? There is inherent noise in the system. There are a lot of limitations in the system. What you see as the final nice print is not what actually you get at the base of the thing. There are a lot of signal processing which goes on before you get that thing. So up to modulo that, a similar job can be done by this kind of MRI things. That's idea. Yes, please.
For accuracy or for performance analysis.
Yeah.
In place of that BER plot.
No, that BER was just for communication problems. Here it's actually, it is PSNR or something that you do.
So can we use histogram plot?
Histogram, and then you have to compare now. How do you compare two histograms? So you look at error plots. That's what if you know the original thing, if you know what's the reconstructed thing, you can compute the mean square error, for example. That's one metric. Several such metrics are there.
Because it also works on counting ones and zeros in the image. Histogram plot, sir.
Yeah. But see, this image, for example, even this will work even if the image was completely gray.
Okay.
That is because we do not really want a histogram to be concentrated, etc. But for example, if I take Haar wavelet transform, if you know Haar wavelet transform, if the histogram is focused on a small, one peak, that's good enough. So some story I am pushing under the carpet. Please read. That paper is an amazing one, though it's not mathematical though. Candace Romberg and Tau. At least I might have made you more hungry to have a good lunch, which is good.
Like even after going, that was the first question that we.
So his question is, what was that original communication failure? I don't know. I was only saying that, look, we don't talk other than what is there in the newspapers about that. I looked at sources to see what is there. I could not find out what the problem was there, and what exactly the problem was. But working with some of these people, not this agency, but some others, the key is that many a times we use equipments which are imported and things like that, and we don't know the details to say, look, this is why it failed. So for example, this particular cases, there is an important block of synchronization where data is there, all the transmissions are there, but somehow you are not able to synchronize. For example, the speed with which relative speed at which your, for example, the object spins or something like that happens, the Doppler shift itself will be high to compensate for the thing that you are looking at. Now, because of that, you may not be able to, for example, adjust to that. So signal may be lost just because we are not correcting the Doppler correctly. One reason. So there are several such reasons. This equipments, I don't know about ISRO, so I can't talk for them. But for other places where they buy French and other equipments, there are these black boxes which gives you a prop signal out. And that is supposed to be the synchronization signal for the rest of the device that you are building. So I asked those people who are using it, how do you know that's correct? Or that's the best way to do that? No, there is no way. It's a black box. You plug it in, and so that's what we talk about it as if there's something sacrosanct inside. We are not talking about what is inside that. Nobody asked the question, okay, what is this communication failure? Tell me, what are you using? There's no secret about this. No, you can just listen to Cassini or Voyagers, those kind of people, and then you can try to figure out. So it is not rocket science in that sense. But still, nobody has inquired. I don't think so.
In a second phase firing, there was a little delay in it. So because of that, it's not followed the trajectory. So because the time loss is over.
Yeah, possible. Yeah, there are a lot of things. But I was only dealing with that communication link about that. You know more about it. You're mechanical.
Can you please suggest some examples of IoT where these concepts can be used? These all concepts.
Yeah. So he's asking, give me some examples where such
IoT examples.
IoT examples where such things can be used.
These all theories which we have studied.
Yeah. So any IoT device, if you, for example, set your mobile phone as an IoT device which takes information and sends it to some other party, right? The link, though you don't see it, when they showed you a Wi-Fi module or a light module or light wave direct light module, you might have done something in the lab, no? With the modules. The backend is exactly doing what we are saying. It sends data, it gets corrupted copies, but it is telling you back what the original data was. So the data is taken, it is not sent as it is, but it is made into some kind of linear combination in a proper field. That's the value which is being sent. Right? And then you use this additional or redundancy is added to the data while being sent. Then you use that redundancy to get back your data. Nobody tells you that it is done, but that's what is the backend which is being done. Second, if your IoT has for example, a temperature sensor, you want to find the temperature of the whole place or something like that. How many devices that you should place to get your field intact? Very closely related to the equation, the questions that we asked. How many equations do we need to solve for an n-length vector? So sensor networks, wherever you have to sense, the idea of compressed sensing that we have suggested can be used. Any communication link in IoT, which is the fundamental and critical link in any IoT device, behind that runs using this techniques that we have come, right? In fact, technology has advanced so much that we are just buying it and doing plug and play, but we should not be limited to that. We should go back and look at what the technology, how does it transport the data to the other side of the thing. Any storage device you encounter is using the technology that we have set. Okay, so I've chosen to just talk about the technology behind the curtain rather than just the application, which you might be seeing in the other set. Did I answer? Okay, then thank you very much. Enjoy your lunch.